Students about thermochemistry, but we are focusing our first lesson on energy. Why do some reactions, like the combustion of fossil fuels or the metabolism of carbohydrates in our body that release a great deal of useful energy, why do they happen? Why do other reactions absorb energy from the environment? Why do some reactions occur very quickly and others don't? So we're going to be looking at energy changes observed when bonds break and new bonds form. This unit or this module, we're going to be looking at energy basics, but specifically when we're looking at energy, we're going to be able to define it, distinguish types of energy, look at the nature of energy changes that accompany chemical and physical changes, distinguish the related properties of heat, thermal energy, and temperature. We're going to explore specific heat capacity, and look at calculations involving heat, specific heat, and temperature change. So chemical changes and the changes that go with it in energy are really important parts of our world. We have reactions when we are metabolizing food, obviously the burning of fossil fuels, the production of useful products from raw materials. This is all part of thermochemistry, which is the study of heat absorbed or released during chemical and physical changes. Energy is a really important part of our daily lives. Check out this cheeseburger from lunch. It gives us the energy that we need to get through the rest of the day. This is a picture of showing us the combustion of gasoline that gives us the energy that moves our car and us between home, school, and work. Coke, a processed form of coal, provides the energy needed to convert iron ore into iron, which is essential for making many of the products that we use daily. So what is energy? Energy is the capacity to supply heat or do work. There's two types of energy, two main types of energy. We have potential energy and we have kinetic energy. Potential energy is the energy that an object has because of its position, composition, or condition. It is stored energy. Kinetic energy is the energy that an object possesses because of motion. And the law of conservation of energy says that the total energy in a system does not change. Energy cannot be created or destroyed. So energy can change from one form to another. So a good example of potential energy would be like a bow and arrow, where when you pull back that string and you have it as far back as you can and you are ready to let it go, like it's as far back as it can go. You have a lot of stored energy. And then as soon as you release it, that stored energy converts into kinetic energy. So potential energy can convert to kinetic energy. The total amount of energy is always the same in the universe. Here's another example where this bike rider, he has kinetic energy going up the hill. As soon as he gets to the top of the hill, he now has no kinetic energy and he has all potential energy, and it will start converting, and he will, as he goes down the hill, he gets less potential energy and more kinetic energy. Same with this girl that's holding onto this ball. This ball right now has all potential energy. And then as soon as she drops this ball, it loses potential energy and it gains kinetic energy. Some other examples of energy conversions in the real world We have water that's at a higher elevation, like in this waterfall at Victoria Falls. It has higher potential energy than water that is at a lower elevation. And as that water falls, some of the potential energy is converted into kinetic energy, that moving energy. We know that we can see that the water is moving faster down here than it is up here because that potential energy is converting. And then we have the Hoover Dam over here where if water flows through generators at the bottom of the dam, then that kinetic energy, that moving energy, is converted into electrical energy and is able to power homes and businesses in a long, that reaches in far areas. Some other forms of energy, like we said, energy can be potential or kinetic, stored energy. Some energy that's stored to be used later, chemical energy that's stored in food and fuel, elastic energy in objects that are stretched, nuclear energy stored in the center of particles, gravitational energy, any energy that's an object that's above the Earth's surface. Kinetic energy, some examples of kinetic energy, movement energy, like thermal energy, energy of moving particles, heat. We know that colder objects move slower than warmer objects. Mechanical energy, energies of objects in motion. Electrical energy, when particles are moving through a wire. Magnetic energy, energy that causes a push or a pull. Then we also have sound energy. So we can hear those sound waves. Light energy, energy that reaches our eyes. All different kinds of energy. So chemical bonds store potential energy. So when we were talking about potential energy and kinetic energy, when we are talking about chemical bonds, that's storing energy. A compound that has lower potential energy is more stable. So compounds want to be at the lowest energy possible. Lower energy is more stable than a compound with higher potential energy. Reactions that form products having lower potential energy than reactants are favored. So, like we said, down here are our products. If they have lower potential energy, those are favored. So exothermic reactions show us that our reactants have higher energy. This shows us that going up, we have higher energy. So if our reactants are up here and our products are down here, our reactants have more energy. And then this graph shows us, well, it takes a little activation energy to make this reaction happen. And then energy, so a little bit of energy is needed to make it happen. This is the energy that's released. And here's our products at a lower energy. And this is as the reaction happens. This is time, our time axis. And so when when it gives off energy, and products are at a lower energy level, this is called an exothermic reaction. That means heat is released, energy is released. Now the other kind of reaction is when our reactants energy start lower and energy is absorbed to make this reaction. So we still have our activation energy. As you can see, it's a greater activation energy. And my products have higher energy than my reactants from where I started. So energy is absorbed. This is called an endothermic reaction. So when products have more energy than the reactants and energy is absorbed, it's an exothermic reaction. So, like we just said, whether it's releasing or absorbing heat, a change that releases heat is called an exothermic reaction. It releases heat. An example would be combustion. Anything that is combusting is going to produce heat. A change that absorbs heat is an endothermic process. An example would be one of those instant cold packs. So these units of energy, we are typically measured in units of calories. Calorie is the amount of energy required to raise 1 gram of water by 1 degree Celsius. So 1 gram of water by 1 degrees Celsius. The calorie, capital C calorie, or large calorie, is commonly used in quantifying food calorie content or food energy content. Is it called a kilocalorie? Now, the SI unit, looking at the metric system of heat, work, and energy, is the joule. So joules and calories are our units used to measure energy. 1 calorie is equal to 4.184 joules, and this is important to know. You need to know this. 1 calorie is equal to 4.184 joules. It's important to know this, just like 1 hour is equal to 60 minutes, 1,000 meters is equal to 1 kilometer. We need to know this conversion. 1 calorie is equal to 4.184 joules. Joules and calories can be reported in the larger unit, kilojoules, kJs, and kilocalories, kcals. So 1,000 joules is equal to 1 kilojoule. 1,000 calories is equal to 1 kilocalorie. And therefore, 1 kilocalorie, because 1 calorie is equal to 4.184 joules, so 1 kilocalorie is equal to 4.184 kilojoules. So again, joules and calories can be interchangeable, looking at converting from one to the other. Calorie is telling us how much energy is needed to raise 1 gram of water by 1 degree Celsius. That's how much energy. Calories are an energy unit. This also tells us the specific heat of water. The specific heat of water is 1 calorie. That's how much energy it takes to heat 1 gram of water by 1 degree Celsius. So let's do a little practice. If we're told that a reaction releases 421 kilojoules of energy, how many kilocalories does this respond to? So we're going to set this up and always start with what we're given. 421 kilojoules. Now we always set this up by, it's what we want over what we've got, or what we're given. So we know that we're given kilojoules. And what do we want? We want kilocalories. Now sometimes we can't just go directly from one to the other, but if we look back at this last slide, we can see that we can go from kilocalories or kilojoules to kilocalories. We know that 1 kilocalorie is equal to 4.184 kilojoules. 4.184 kilojoules is what I've got, right? Because I've got kilojoules, and we need our units to be diagonal from one another so that they can cancel out. It's equal to 1 kilocalorie. So because these units are diagonal from one another, they're going to cancel out. So now I just need to get my calculator and do 421 times it by 1, and then divide it by 421 times 1, and divide it by 4.184 to get, my calculator tells me that it's 100.6214, and then there's a whole bunch more numbers, but I'm going to stop there, and we need to find out how many significant figures we have. Because I started with 3 significant figures, I need to end with 3. So I need to go, okay, 1, 2, 3. And what is that 6 going to do to that 100? It's going to round it up to 101 kcals. Here are some more practice problems. Why don't you pause the video and try to do these 4 on your own, and then check back in and we'll do them together to make sure you got the right answer. All right, well, let's look at A. We're starting with 42 joules. So that's what I'm given, that's what I've got. What do I want? I want to get to calories. So let's set up our first part. So what do I want? And I can go from, I know joules and calories, I can go right from one to the other. So what do I want? Calories. What have I got? Joules. We know that 1 calorie is equal to 4.184 joules. So in my calculator, I'm going to do 42 times 1 and then divide it by 4.184, and I got 10.038. But again, I started with 2 significant figures, so I need to finish with 2. I'm going to go 1, 2. That 0 is not at the 10th 0 is not going to change my 10, so it's just going to be 10. My joules cancel, 10 calories. All right, let's look at letter B. We'll change colors here, and we'll start with 55.6, which is 3 significant figures, kcals, kcals. Okay, so what do I want? Calories. What have I got? I've got kcals. And we know that 1 kilocalorie is equal to 1,000 calories. So if we just do the math and do 55.6 times 1,000, we would get 55,600 calories. And if we look, again, we only had 3 sig figs to start with, and we only have 3 sig figs to end with, because again, these zeros are just placeholders. And our kcals and kcals canceled out. All right, let's look at letter C. I'm starting with 326 kilocalories, and it wants to convert to kilojoules. And luckily, we can just say, okay, what do I want? Kilojoules. What have I got? Kilocalories. We know that 1 kilocalorie is equal to 4.184 kilojoules. So now we just need to plug that in. And my calculator tells me 1,363.984. But again, we need to look at, well, I started with 3 significant figures, so I need to end with 3 significant figures. So 1,363, and then is that 3 going to do anything to that 6? No. So 1,360, we do have to put a 0 as a placeholder there, because 1,363 would round down to 1,360. I can't just make it 136. 136 is nowhere near 1,360. So 1,360 kilojoules. Great job. And let's look at our final practice. So for this last one, we're starting with kilocalories. Now I want to get to joules. Well, we know that we can go kilocalories to kilojoules, and then we can go from kilojoules to joules. So this is going to be a 2-part. So I'm going to say, what do I want? I'm going to go to, well, what do I want? I want kilojoules. I know that's not what I really want, but I know that I can go from calories right? We know that 1 kilocalorie is 4.184 kilojoules. So that gets rid of my kilocalories. But I need to do one more. I need to get rid of kilocalories now. Kilocalories is down here. What do I really want? I want joules. What have I got though? I had to do an intermediate, get rid of those kilojoules, right? And we know that 1 kilojoule is 1,000 joules. So now we just need to plug this into our calculator. So I would do 25.6 times 4.184 times 1,000. So we would multiply all across, and we would divide by the bottom. Underneath I've got 1 times 1, so I'm going to divide by 1. So I'm going to get 1, 0, so let's write down our whole big number that we get. 107,110.4 is what my calculator shows. So now let's look back at what we started with. I started with 3 significant figures. So I need to end with 3 significant figures. 107, that's my first 3. That 1 is not going to, that 1 will not raise that 7 up to an 8. So we're leaving it 107,000. Right, I still have to put my 0 placeholders in there. And what is it? Joules. All right, hopefully you're feeling good about that. So when we think about energy changes that happens in reactions, we really need to think about what is chemistry and how do these bonds break and form. And really what it comes to, really the heart of chemistry, is that in order for molecules to come together and react, there needs to be collisions. So two molecules need to either collide with one another to break bonds, or they need to come and if they're trying to form bonds, they need to come close to one another to form bonds. So they need to collide in order to react. So bonds are broken in the reactants and new bonds are formed in the products. So here's an example. Bonds breaking always requires energy. In order to break this bond, energy is needed to separate them. So to cleave or to break this bond, so to cleave means to break. We need to add energy to it. Again, looking at this reaction, if I have a molecule of chlorine, so here I have Cl2. And we can see this is a molecule of chlorine. Energy is needed, so I need to add energy to, on my reactant side, right? I need to add energy to break it. And we can see that this bond cleaves or it breaks. We can just put a line right down here. We know chlorine has 7 valence electrons. And let's see, this chlorine has 1 over on the left, 1 on the right. So it forms that bond right there. But when it cleaves or when it breaks, over here, I have 2 atoms of chlorine that are now separated. And we can see that they each have they took their electron back. He has 7 and he has 7. And again, we know that by showing the Lewis dot diagrams of these, that each chlorine in my reactants had 7 dots, and the lone dot on each one formed that pair. And then over on the right-hand side, we know that the 7 dot 7, because it's in the group 7A, which are our halogens. And so this is how we represent the atomic chlorine. And so we're told here that in order to break that bond, it actually took 58 kilocalories for 1 mole of diatomic chlorine to separate that. So instead of just writing energy, what energy needed, we could be specific and we could say 58 kcals per mole plus, or needed to break apart that diatomic chlorine to break that bond and separate it into individual atoms. We can also do this in reverse. Instead of breaking a bond, I can form a bond. So when we form bonds, we release energy. So here I have my Lewis dot of atomic chlorine, and I want to add my also individual chlorine atom to form this Cl2, or so we can see our 7 dots. These dots are going to align and form that bond right here. We also can represent it like this, which we also know is Cl2. But when we form that bond, we know that 58 kilocalories is going to be released. So over, if that means it's released, that means it's in my products. So I could say plus 58 kcals per mole in my products. So looking at this one more time, if it's released, we know that my energy is on the it's on the product side, and we also know that energy that's being released is an exothermic reaction. On the flip side, if we are needing energy to break a bond, and therefore the energy is in my reactants, then this is absorbing energy, and therefore this is an endothermic reaction because energy is needed to break that bond. So this is telling us this is breaking a bond is endothermic, it's absorbing energy. As opposed to if we are forming a bond here, again, I've got 2 chlorine atoms that we are going to form this bond. That's an exothermic reaction, and it releases heat. So my heat being released, we show it that it's in the products. So what we're ultimately looking at here is what's called bond dissociation energy. And dissociation means to separate. So the dissociation energy, or the energy that's needed to separate or break a bond, is shown by this symbol of delta H. And delta H is that energy that's absorbed or released in a reaction, which is called the heat of formation. I'm sorry, I didn't mean heat of formation. Heat of reaction is this delta H. How much energy is required to absorb or is required to make this reaction happen? So if we go back to this last slide, we saw that 58 kcals was required to break that bond. But then also notice that that same number, the 58 kcals, was required to form the bond. So whether it's forming or releasing, whether it's in the reactants or the products, it's that same energy, amount of energy is required to break or to form that bond. So that delta H of a reaction, that heat that's of that reaction is also called the enthalpy change. Enthalpy simply means the heat change. And we show that when energy is absorbed, we said that it's an endothermic reaction. And that delta H is positive. So in referencing this Cl2, if we break that bond and we say it's endothermic, we have a positive. It takes 58 kcals of energy, of heat, to break that bond. It's a positive, delta H is positive. Now, when energy is released, so when I go backwards and I take my two atoms and I form a bond, we know that forming a bond, like we just said, is exothermic. That negative, or that delta H, is negative. So notice it's the same number, it's the same amount of heat, but if it's exothermic, it's represented, that delta H, as a negative value. And if we break a bond and it's an endothermic reaction, it is shown as a positive value. So again, whenever we have an endothermic reaction, whenever we are cleaving or breaking bonds, delta H will always be positive. And in reverse, whenever we form a bond and it's an exothermic reaction, delta H will always be negative. So delta H, when it's positive and it's endothermic, think of it as energy that is being inputted into the reaction. So it is on the reactants side. And when we have exothermic and it's being released, think of being released as part of the product side. So enthalpy, one last time, is more like, it's a thermodynamics term. Yeah, a thermodynamic process. The bond dissociation energy, which I wrote up here, and I apologize for the mess. My computer screen does not like my stylus. The bond dissociation energy, again, is the amount of energy needed to break or form a bond. So delta H is our heat needed to break a covalent bond between the two atoms or to form it. Bond dissociation energies are positive when it's endothermic. So that means if it's positive, that my delta H is greater than 0. So in this case, if I want to break that bond, or if I want to cleave it, it's going to be a endothermic, right? Because endothermic means I need to have energy on this side, and it tells me that the delta H is positive 104 kilocalories. So it's going to take, on my reactant side, 104 kilocalories of energy to break that bond, to have 2 atoms of hydrogen in my product. Bond formation, is always negative. Negative means exothermic, so that means that my delta H is less than 0, which is going to be a negative value. So to take my 2 atoms of hydrogen and have it form H2, which we represent as like this, H-H, showing that those 2 electrons that form a single bond, we see that it is a negative value of 104. So same number, opposite signs, because again, when I form a bond, it releases, which is like having this energy that's being released as part of my product. 104 kcals. As we look at bond dissociation energy, we can also look at a periodic trend. And we can also see that the stronger the bond, the higher its bond dissociation energy is. So if we look at elements in the same group, like fluorine, chlorine, bromine, and iodine, which are all part of the halogens, group 7. Fluorine is at the top of the group, followed by chlorine, and then bromine, and then iodine. We can see that fluorine has a positive 136. The hydrogen chlorine is 103. Bromine, 88. Iodine hydrogen, 71. So we can see that the bond association energy is highest up at fluorine, right? This is the greatest number. So it decreases going down. So if this is my fluorine is my greatest, that means it's going to take it's the strongest bond if it requires the most amount of energy to break that. So if we have the highest bond association energy, it's going to take the greatest amount of effort to break that bond. It's going to take more heat energy to break stronger bonds. And so if we look at fluorine up here at the very top, and again, if we were to connect fluorine to hydrogen, chlorine to hydrogen, bromine to hydrogen, iodine to hydrogen. So up here, if I look at my hydrogen fluorine, fluorine is my smallest atom. So those protons are going to be attract most electronegative, right? It's the most electronegative of this whole group 7A halogens. Those protons are highly, highly attracted and closest to the electrons. So that pull is very strong, which means, again, stronger bonds, we need more heat energy to break them. And we can see that we need more heat energy. 136 kcals of energy are needed to break that strongest bond. And then the next smallest one is chlorine. And we can see that chlorine is the next highest amount of heat energy needed to break that bond at 103. And then bromine, and then iodine is my biggest atom. So put my biggest atom, and those protons are much further away than the electrons. That pull is a lot weaker than fluorine. So since it's my biggest atom, it's the least electronegative of these four. So it's going to take less energy to break that bond. So it's the weakest bond of those. Here we have a chart, and this is our bond dissociation values. And we can tell their dissociation values because bond dissociation means to break bonds. And dissociation values are, if you're breaking them, it's endothermic. And endothermic are positive values. And we can see here that these are all positive values. So this wants us to write the equation for the formation of HCl from H and Cl atoms, classified as endothermic or exothermic, and give the delta H using the values in the table above. So we're going to form HCl, which means HCl will be a product. Now, if I were to make my reactants hydrogen, I can't just have hydrogen by itself, right? Because hydrogen is diatomic. We have to have H2. And we're going to add chlorine, which is Cl2. So I'm actually going to back this up 1 minute. If we just looked at the formation of HCl from a hydrogen atom and a chlorine atom, if I looked at just hydrogen with one valence electron plus chlorine with, we know chlorine has 7, 6, 7. And I'm going to do my little arrow. I'm going to do an arrow like this. Sorry, it's bent. To form HCl, where there's my bond. 1, 2, 3, 4, 5, 6. So we can see here that I have a hydrogen atom, a chlorine atom, and a hydrogen chloride molecule. Jeez, this writing is terrible. So after backing it up, we have our hydrogen atom, our chlorine atom. They are forming an HCl. So again, we need to look at this and go, oh, it's forming, it's exothermic, it's releasing energy. And while this chart that we're using here is for dissociation energy, so this is showing us bond breaking energies, but remember, those values are the same quantity, it's just a flip sign. So if I look up HCl, to break HCl requires 103 kilocalories per mole of energy to absorb to break it. But to form it, again, forming is exothermic, forming is negative. That just means that over here, my delta H is going to be negative 103 kilocalories per mole. Now, if I wanted to write this a correct balanced equation, we need to be able to recognize that hydrogen is one of those lucky 7 that needs to be diatomic. Chlorine also needs to be diatomic. And so therefore it needs to be H2 and Cl2. And then to balance HCl, we would need a 2 right here. But we also would still have the same, we're still forming HCl. It's still the same delta H. And it is still exothermic. Okay, it's time for you to try. A, B, and C, we want you to give the delta H for each reaction and classify them as endo or exothermic. So when you think you're done, pop back on and we will check them together. Okay, hopefully you have paused and taken a minute, but let's look at HBr. So here we are breaking a bond. And if we look over here at our dissociation energies chart, we're going to find HBr and notice that the delta H is plus 88 kilocalories per mole. Now remember, that is if we are, oh, here we go. Remember, dissociation is endothermic, and if we are, and that's breaking, right? That's cleaving or breaking. Because it takes energy, which is positive. It takes energy to break a bond. So that is what we're doing. We are breaking a bond. So we are cleaving it. We are disassociating it. So we have breaking. I'm going to write break. We're breaking it. So if I look at A, we would say that my delta H is positive, right? If we are breaking it, it's positive. 88 kilocalories per mole. And we're breaking it, so it is endothermic. I'm just going to write endothermic. So it is absorbing that energy. And that means that that energy is on the reactant side, that plus 88 kilocalories per mole. Now let's look at letter B. Letter B is forming a bond. I have one atom plus another atom to form a bond. So I'm going to write forming. Remember, forming is exothermic. So if I look at B, I'm going to find that HF, let's look here. Now, again, this is a dissociation chart. So this is always looking at endothermic. Yes, it says that it's positive, but because it's forming an exothermic, we're just going to flip that sign. So we're going to say that my delta H is negative 136 kilocalories per mole. It's exothermic, and that means the energy is being released. Also, we would show that that energy, that negative 136, is in the products because it's being released. And then let's look at letter C. Go purple here. C. We have HOH and then my arrow. So we are taking water, we are breaking it. So again, we have another breaking. So I'm going to find HOH right here. And yes, we are disassociating it. We are breaking it. It is endothermic. And so we keep that positive. Delta H, positive 119 kilocalories per mole. It is endothermic. And that energy is being absorbed. All right, good job. Here's something to look at. Here I have two different molecules, and we want to know which of these bonds would have a higher dissociation energy and why. So here we're looking at carbon fluorine. Well, we've got CH3F, and here we have CH3Cl. So here we're specifically looking at the carbon fluorine bond versus the carbon chlorine bond, and to see which one has a higher bond dissociation energy. Well, if you remember and look at the periodic table and we look at our halogens, because fluorine and chlorine are both in the same family, halogens. And we have fluorine is at the very top of the column, and then chlorine, and then bromine, and then iodine. And we said earlier that as you go up a column or a family, that bond dissociation energy increases. And so the carbon fluoride, if we were to add a carbon to any of these, this bond is going to be a stronger bond because fluorine is smaller than chlorine, so it makes it more electronegative. Those protons are more attracted, they're closer to the other electrons, and the chlorine is further away. If you think fluorine has two shells of electrons, and chlorine has, it's in my third period, so it's further away, it's got more distance, and so that attraction is weaker. Fluorine has, like I said, it's smaller, and more electronegative. I'm going to say electronegative for an E negative because my pen just does not work nicely on here. So let's look at these. So I have letter A, or letter B. Which one of these would have a higher bond dissociation energy and why? Take a second and investigate these two and tell me what you think. All right, hopefully you took a minute to look at the differences between these two molecules. And again, we're looking at carbon to iodine and carbon to bromine. So thinking back to that last example, when we looked at our halogens, which was group 7A, we have fluorine at the top, and then chlorine, and then bromine, and then iodine. We're just going to use that. Oh, there we go. And so remember that as we go up a column, the dissociation energy increases because those atoms are getting smaller. So it takes more energy to break those bonds. The higher we go, the stronger they are, the more energy, the more dissociation energy is needed to break those bonds. So if I'm comparing iodine versus bromine, bromine is going to have the greater dissociation energy. So stronger bond. There. So the higher you go, so bromine is higher than iodine, it's a stronger bond, which means it has a higher bond dissociation energy. Now, if we were to look at the next two examples, we have H bonded to O, we have H bonded to S. Now, if we were to look at H bonded to O and H bonded to S, we can see that O and S in group 6A, we have oxygen and then sulfur and then selenium. So again, as we go up a family or up a column, the bond dissociation energy increases because those smaller atoms have stronger bonds. So oxygen bonded to hydrogen is much stronger than sulfur bonded to hydrogen. So we here has a stronger bond. It is more electronegative. It has a higher bond dissociation energy. Same reason why carbon to bromine was the correct answer. Stronger bond. So we're going to say the same thing for right here. Higher bond dissociation energy. And both of these are more electronegative. So expanding on that, we're going to look at thermochemical equations. And a thermochemical equation is basically just a balanced equation with the delta H included. And you all are hopefully feeling good about balancing equations. So we just need to make sure that we are balanced and, come on, and include the delta H, all in the same line. So on your paper, it asks for the combustion of methane. So we need to write CH4, CH4 is methane, and we include that it's in the gas stage, plus two O2s, two oxygens. Again, if oxygen is by itself, it's not just O, it's O2. It's part of the 7 diatomic molecules. And if you look on your periodic table, it makes number 7. So if you looked up nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and hydrogen, of course, is added to that. So it's a 7 and then that hydrogen. Or I always would tell my Gen Chem students, Brinkelhoff, B-R-I, oh, if you don't know that, B-R-I-N-C-L, Brinkelhoff. If you can remember Brinkelhoff, all of these are diatomic when they are by themselves in nature. So we have CH4, we have oxygen, and those combine to form carbon dioxide gas and 2 H2Os. And if you were to look at that, that is a balanced equation. And then right at the end of that balanced equation, we include the delta H, which is negative 213 kilocalories per mole. That tells me that negative tells me that is exothermic. Heat is released to the surroundings. So we know exothermic, again, heat releasing to the surroundings. It's giving off heat. And that also tells us that my reactants started at a higher energy. And as the reaction takes place, this is called our activation energy, E activation, ACT activation, E for energy, activation energy. And then my products end down here. So they have a lower energy than where my reactant started. And this difference between the reactant to the product, see how it went down. So that's a negative, telling me that it's exothermic. This delta H went down, so it's negative. It is giving off that heat. So the heat of reaction, the delta H is negative, telling me that it's exothermic. Let's look at another one. The thermochemical equation for photosynthesis. So photosynthesis, I'm going to have 6 moles of carbon dioxide gas plus 6 moles of water, liquid water, and that's going to combine to create my glucose, which is C6H12O6 aqueous, plus 6 moles of oxygen gas. And the delta H for this thermochemical equation is plus 678 kilocalories per mole. So heat is absorbed. Again, we know because it's a positive that it's an endothermic reaction. An endothermic reaction, again, remember my reactants have a low energy. Again, because if this is low energy down here on my y-axis, energy increases as we go up. So I have low reactant energy, I have higher energy in my products. So my delta H is between reactants here and products here. This difference is my delta H. So my delta H is positive. Heat is absorbed. My products, we are absorbing heat energy from the surroundings to the system. Okay, so now let's look at this one. I have 2 moles of NH3 that are gas, and we can see that it is decomposing to 3 moles of H2 and nitrogen gas with a delta H of plus 22.0 kilocalories, and that should say per mole. Now, based off of this, I want you to see if you can answer these 4 questions. So pause the video, see if you can answer those, look back at your notes, and then press play and we can go over the answers. So this whole thing right here is my thermochemical equation. Okay, we can tell, again, that because I have 1 reactant, and then the arrow, that this is a decomposition reaction. We can also tell that, sorry, that says decomp for decomposition. We can also tell that this plus is that it is endothermic because it's positive. So here we go. We can go right down here. We can say it's endothermic because it's a positive delta H. My delta H, remember that delta H stands for, this is my enthalpy, how much heat. Which is equal to heat. And since it's positive, again, that means that heat is needed to break apart those bonds. So this is going to look like a graph like this where my reactants are down here. And remember my y-axis, I'm going to do E for enthalpy increases. So my reactants are low and my products are going to be up here. So my delta H will be positive. So my reactants are lower in energy. So the reactants are lower in energy. Which bonds are stronger? The reactants or the products? Well, because it's endothermic, my reactants have stronger bonds, right? Because we need to, when we have a plus positive enthalpy, breaking those bonds, it's going to take a lot of energy. So my reactants, and is heat being released or absorbed? Well, because it's a positive delta H, we know that my that's telling me that it's endothermic and heat is being absorbed, and therefore they need to be on the reactant side. So you look at the sign of the delta H, and if it's positive, it's endothermic, which means it is being absorbed. All right, let's look at this problem. We're going to get even more in depth. So we have a thermochemical equation here looking at the combustion of propane, which is C3H8. And it tells us that our delta H is negative 531 kilocalories per mole. And this is a balanced equation. For every 1 mole of propane combined with 5 moles of oxygen, it creates 3 moles of carbon dioxide gas and 4 moles of water. So what can we do with this? Well, if we look at this problem, it says the combustion of propane with oxygen, according to the given balanced chemical equation, releases 531 kilocalories. So because it says it releases, remember that's a negative value. So this is an exothermic reaction. Again, remember exothermic, where my reactants have a higher energy and then they release energy. So my reactants are here, my products are there. This is a negative delta H. Okay. Then we want to know how many kilocalories of energy are released when 0.750 moles of propane are burned. So this thermochemical equation tells us that when 1 mole of propane is burned, here's how much heat energy is released. How do we figure out if we're at 0.75 moles? Well, we just have to do look at our stoichiometric ratio, and everything is given to us. So we just need to start off with what are we given in the problem. Okay, so that's 0.750 moles of C3H8. And again, what do we want? We want kilocalories. What have we got? We've got moles of C3H8. And we're going to look and say, okay, what is the kcal? Oh, we said that the kcal that we're given is negative 531. All right, I moved that. Negative 531 for every 1 mole of propane. Again, I just used that balanced ratio right in front of the C3H8 is 1. And then I'm just going to multiply. I'm going to do 0.750 times negative 531 divided by 1. Remember, it's what we want over what we got, that ratio. And we're going to get negative 398.25, I believe my calculator says. And we need to look and say, okay, I started with 3 significant figures, SF or sig figs. So we need to end with 3. So I'm going to go 1, 2, 3, 398 So negative 398 kcals. Now, how many kilocalories of energy are released when 1 mole of oxygen reacts with propane? Well, right now we have 5 moles of oxygen releasing or being used. But what about if 1 mole? So we need to start, okay, what are we given? We're starting with 1 mole of O2. What do we want? Kcals. What have we got? We've got moles of oxygen. So we just need to look at this ratio now. Again, same kcals up here at the top, negative 530, come on, 1 for every, over here, 5 moles of oxygen. That's our stoichiometric ratio that's given to us in the problem. And then I'm just going to plug that into my calculator. So I'm going to do 1 times negative 531 divided by 5. And I should get, your calculator should say negative 106.2. And I need to look and say, okay, I started with 3 sig figs. So I need to end with 3. 106.2 is going to round to negative 106 kcals because moles of oxygen cancel out. Great. Hopefully you feel good about that. Let's move on. All right, let's look at another example. So we have another thermochemical equation here that's telling us, let's change here, using the given value of delta H in the balanced thermochemical equation for the reaction of magnesium with water, how many kilocalories of energy are released when 4 grams of magnesium are used? So this is very similar to the last one, except for we were told moles, because remember, in our balanced thermochemical equation, like 1 mole of magnesium reacts with 2 moles of water to create 1 mole of magnesium hydroxide and 1 mole of hydrogen gas. So this is our stoichiometric ratio. We're looking at moles. Here I'm starting with grams. So this is my starting point, 4.00 grams of magnesium. Now hopefully you remember from Gen Chem 1. Anytime I have grams of something, I need to get to moles of something. And by doing that, I just need to look at my periodic table and look at that molar mass. So what do I want? I want moles of magnesium. What have I got? I've got grams of magnesium. And so I'm just going to look at my periodic table, and for every 1 mole of magnesium, there is 24.3 grams of magnesium. Okay, so that'll get us to my grams and grams. So now I'm at moles of magnesium. Now I can do my next step. Once I have moles of magnesium, we want to get to kilocalories. So I'm going to say, okay, for every 1 mole of magnesium, according to my stoichiometric ratio, so what have I got? I've got 1 mole of magnesium, and it releases negative 83.9 kcals. Okay, so that means that my moles and moles will cancel and I'll be left with kcals. So we're going to multiply all across the top, and then we're going to multiply all across the bottom, and we're going to do our total top divided by total bottom. So I'm going to do 4 times 1 times negative 83.9, and let's see what we get. And when I did my total top, I got negative 335.6. My total bottom was 24.3, and then that top divided by bottom, I got negative 13.81069959. And I need to think back to sig figs now. So if I look at sig figs, I started with 3 sig figs. So I need to end with 3. So 1, 2, 3. That 1 is not going to do anything to that 8. So I'm going to leave it at negative 13.8 kcals. Good work. All right, we have 3 more to go, looking at the fermentation of glucose. So we have glucose. All right, let's look at these glucose questions here. How many kilocalories of energy are released from 6 moles of glucose? So this is my glucose here. I've got C6H12O6. All right, so I'm starting with 6.0 mole of C6H12O6. Okay, so what do I want? I want kcals. What have I got? I've got moles of glucose. Okay, so let's look at our balanced equation. How many moles of glucose does my balanced equation have? 1. And what does it say my delta H is? Is negative 16. So I'm going to plug in 6 times negative 16 divided by 1. My moles of glucose cancel out. And I should get negative 96 kcals. And I started with 2 sig figs, so I'm ending with 2 sig figs. Okay, let's look at number 2, or letter B. How many kilocalories of energy released when 1 mole of ethanol is formed? Okay, so here is my ethanol. So let's start with my 1.0 moles of C2H6O. All right, and let's look at my stoichiometric ratio. Again, I need moles of ethanol on the bottom, and I have 2. I'm going to say 2 moles of C2H6O. And again, we're using the same delta H, negative 16 kcals. And when I do this math, so if I do 1 times negative 16 divided by 2, I should get negative 8. And I need 2 sig figs, so I'm going to say negative 8.0 kcals. And let's do letter C. How many kcals of energy released from 20 grams of glucose? Okay, so we're starting with grams. And again, hopefully you go, oh wait, grams. Always if you start with something, you gotta get to moles. So 20.0 grams of glucose. So C6H12O6. And if we look up here, what's nice is they told us the molar mass of glucose at the very top here. If they didn't, we would have to go, okay, 6 carbons, and carbon weighs 12, so 12 times 6 plus 12 H's. Each H is 1.01. Did I say that right? 6 carbons. 6, yeah, each carbon is 12. 1.01, and then oxygen, 6 oxygens, and each oxygen is 16 times 6. So we'd have to add all that up together. But what's nice is they told it to us. So because I started with, what do I want? I want moles. 1 mole. I'm just going to write G for glucose. No. I'm just writing glucose. 1 mole of glucose has a mass of 180.2 grams. Oh. Grams of glucose. And then finally, so that got rid of my grams. I'm at moles of glucose, but what do I want? I want kcals. What have I got? I've got moles of glucose. So I just need to look at that ratio again, and it's the same ratio that we did for number 1. Negative 16 kcals for 1 mole of glucose. And when I do the math, I'm going to do 20 times 1 times negative 16, all divided by 180.2. Let's see what we get. All right, and then again, looking at 3 significant figures. Oops. 3 significant figures, you should get 1.78, I believe is what I got. Negative 1.78 kcals. All right. Hopefully you're feeling pretty good about this. Awesome work. So take a break before your next lesson where we talk about energy diagrams, but we were a little bit sneaky and we already talked a little bit about energy diagrams. So you're going to be prepared for this next lecture.